chapter 15, we have three main rules that we're going to talk about. Number one, we have the general addition rule. This says that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. That's a big deal. Last time it was just the addition parts, but I told you they have to be disjointed, meaning there is no overlap. There is no and. They don't share anything. But in this case, if they do share something, I can't count it twice. The example let's see. Number 2, the general multiplication rule. In this example, or in this formula, last time it was A times B, but now we have a special character that we have left over. The probability of A and B occurring will be the probability of A times the probability of B given that A has already occurred. This is conditional probability, which we'll talk about in just a minute, meaning that the probability of B has now changed because A has already taken place. In the last general multiplication rule, or just the multiplication rule previously, you said if they're independent, you can just multiply their probabilities together because the fact that A occurs doesn't change the probability of B, right? So when they do change, I have to keep into account that when I work these things out, the probability of B given A changes because of what happens. Third example, we're looking at conditional probability. Let's be really clear. This general multiplication rule and the conditional probability formula are exactly the same formula, which is why you don't see both of them written on your formula sheet. On your formula sheet, you will see this one written and this one written. But note, that really essentially gives me all of these. The conditional probability says that the probability that B occurs given that A has already occurred is equal to the probability of both of them occurring at the same time divided by the probability of whatever the condition is. Here we have it as A. Be careful. I could write this out as the probability of A given B, and that would just put B on the bottom. Be careful. Don't get stuck into the formulas being A's and B's and C's. No, you need to put it into place. What was the condition? What was happening before that had to happen, right? In this case, I drew an ace out of the deck, which reduced the number of cards I had, total, and it reduced the number of aces in the deck. And we'll do some examples today to kind of how do we plug into this formula and work it out. But these are the three main ideas, the main formulas in this chapter. Any questions about these? We have another section over here. This is a separate set because this doesn't necessarily, it's not a formula for calculating things. It's a formula for, I want to be able to say, here's two events. I'd like to know if those things are independent or not. We have two ways of justifying that. Number one, if the probability of B occurring given that A happens, has already happened, if that's equal to just the probability of B in general, like it didn't change probabilities, well, it means that the event outcome had no effect, which is by definition independent. We already knew one way. I told you last time the multiplication rule we used. If you multiplied the probability of A and B together, and that was the exact same thing as the probability of A and B occurring, you knew that they would be independent. We were using that in a different way last time, but now if I needed to check, if I had A and B over here, and I had A and I had B, and if I were to multiply them together, and if I could see if they're equal, you have independence. You have justifiable independence, right? Now this is not logical speaking. We're not speaking logically. We are speaking in terms of mathematics. Are they mathematically independent? Do the probabilities work out that way? Sometimes kind of trying to reason in your head is not a worthwhile task because I really don't care about that. I want to know, do the numbers work out that way? Are they independent in a mathematical sense? The probabilities don't change when this thing occurs. Does that make sense a little bit? Any questions about these formulas? If you haven't read chapter 15 yet, I would highly recommend doing that. There's a lot of information here. Being able to see the examples they do in the book does provide a lot of clarity. If we did it this way, the probability of what if you did the probability of getting an ace or a red card? What would that be? It's 28 out of 52. Logically, we can all reason through this. Why is it not 30 out of 52? Because correct. So you're counting them twice. So we'd say, well, the probability of getting their ace is 4 out of 52, plus the probability of getting a red card, which is 26 out of 52, but minus the probability that they both happen at the same time, ace and being red. Well, there's two aces that are red cards, and so we end up with, instead of 30, we end up with 28 out of 52 cards, right? So all the red ones plus the two black aces. And so that's how you would consider this problem. This is a general rule, meaning there is no circumstance that would prevent this one from being true. This one is true even for disjointed events, right? It's just that the and part is 0. So it still works. It's just that part of it would be minus 0, and I would be back to A plus B again, right? Same kind of thing. So the next example would be the probability of an ace on my first try and an ace on my second try, right? So we talked about two events occurring, right, in sequence. And with the OR question, it wasn't that you had two things occurring. It was just the fact that you're going to do one thing, and you wanted to know the chances of that one thing occurring when you could have those outcomes occur at the same time. With this one, I want to know if I did two things back to back, what would the probability be? No. This is without replacement. Okay? In this case, we are, on purpose, going to discuss what happens when I do something like this. And here again, logically, we can all reason through what's about to happen. What's the probability of drawing my first ace?
4 out of 52.
It's clearly 4 out of 52. Right? So pulled an ace out. What's the probability that I draw my second ace given the fact that I already drew an ace out the first time? 3 out of 51. Logically reasoning this out, I can actually calculate that kind of thing, right? I don't even need to be honest with you, you probably didn't even realize you were using the formula because it's so logical. And be careful, sometimes you're going to have to stick with this because there is no logic. It will simply be numbers, and you'll have to work out probabilities and plug them into formulas and things like that. And we'll get to those in just a little bit.
All right, we're going to work through just a few of these problems and kind of just get you started and make sure that we know what we're talking about here. And so we're going to look at number 3. Remember our formulas, our general addition rule basically started out looking like this. The probability of A or B was equal to the probability of A plus the probability of B minus the probability of A and B. Essentially what this is this allows me to add them up, but I'm going to subtract out the parts that I counted twice. And so in this case, we are looking at a survey revealed that 34% of people interested about books, 47% by TV, 19% by both. What is the probability that person will be interested about books or TV, right? So A would be books and B would be TV. And so this would be really straightforward. It's literally as easy as it sounds, right? 0.34 plus 0.47. However, we counted several people twice because they checked both the books and the TV. And so we're going to subtract out the 0.19, which is equal to 0.62, right? It's just a matter of applying the rule when we see it's A or B. I need to make sure that if there is an overlapping section, then I need to actually be able to subtract out of that. And so if I go into, let's look at number 5. Okay, 4 is just like number 3, so you treat that the same way. Number 5 is a little bit different. I want to talk about using Venn diagrams, right? And so if we create a Venn diagram, let's call this one the Spanish, this is going to be the French, this is going to be obviously both. There is a percent, there's 22% of the population in the Spanish category, and then there is 5% in the French category, and there is 3% in both. Now, with Venn diagrams, what we know is that inside the circle that, say, is for Spanish, we know that everything inside of the circle must add up to the total of 22%. Well, I've already got 3% in this circle. I've also got 3% in the French circle. No matter how many different ways I break this up, I can only add up to 22%, which leaves 19% out here and 2% out here, right? Obviously, that I still have a 22% together, gives me 22% speak Spanish. In the circle out here, but outside the French circle where we have the 19%, this is the students that speak Spanish, but not French. Just in the same way, over here, we have the students that speak French, but not Spanish. And so something that students tend to forget about a lot is the fact that in a Venn diagram, the circles aren't always the sum total. We know that if we add 19, 3, and 2, we're going to get a total of 24%. That leaves 76% of the students at this particular school do not speak Spanish, nor do they speak French, right? Only 24% speak those languages. Whether you speak them both or just one of them, 76% of the students at this school don't speak either one of these languages. Now, that's not part of the question. The part of the question was really simple. It was which part do students speak only Spanish, right? Not French, but just Spanish. And we found that just right there. Okay, and that makes it pretty straightforward. Okay, the other thing I'll talk about, I'm not going to kind of do for you, I want you to give a chance to work this out, is number 6. Okay, this is a conditional probability, and we know that the probability for conditional, it looks like this. It's probability of, in this case, we're trying to find it's a 3 given that it is not a face card, right? So we're going to say probability is a 3 given that it is not, that's the symbol for not, a face card. If I use my formula, then it would work like this. Now I'm using the formula from the video or from the notes where you have the conditional probability. Whether you looked that up in the formula sheet or if you looked up in your chapter or you watched the earlier video, hopefully literally it was in this video when I talked about the original statements, the original formulas. It looks like this, right? It's the probability of 3 and not being a face card, right? I want to find the number of cards that fit that group. And I want to talk about the probability of just not being a face card, right? Here again, a 3 is not a face card. So the question would be, how many cards in the deck, or how many out of 52 would be equivalent to getting a 3 and not a face card? Well, remember, the probability that that happens would be 3 out of 52. How many possible non-face cards are there? Well, there's 3 face cards, a jack, a queen, and a king for a deck of cards. There are 4 different suits. If you're not familiar with cards, let me encourage you either to go online, just pull up some pictures, or grab a deck of cards if you have any at home and check them out. We're going to be talking about cards a lot. Okay, I'm going to leave it here. Hopefully you can kind of take this. Try all 6 of these questions, and we'll pick up tomorrow. If you have any questions about this, please feel free to email me, and I'll be happy to get back with you as soon as I can.